Welcome to lecture 42. In this lecture, I will be talking about corrections to the magnetic moment of the electron. Recall that in the last lecture, we discussed the magnetic moment of the electron based on the Dirac equation. Because of the half-integer spin, the correction factor that one would classically expect has a name called g, and that g value for the Dirac equation is 2 in the classical approximation where we use the Dirac equation for describing the electron. In this lecture, we will start considering quantum field theory effects that go beyond the Dirac equation to calculate corrections to g-2. Recall that the Hamiltonian that gives rise to the magnetic moment of the electron is given by the coupling between the electron that is described by the spin of psi and the photon that's given by the gauge field A. That coupling term is the same that appears in the QED action, in particular the meta part, which is psi bar d slash plus IA A slash psi. So recall that these are the same. And if we consider QFT corrections, then effectively it will change the fermion gauge field coupling that appears in the Hamiltonian. So what we want to set up is we want to calculate loop corrections in perturbation theory, meaning for small values of the electron charge E, to the fermion gauge field coupling. For the classical theory, that was just psi bar A slash psi, which I have written out by undoing the slash notation. So I write gamma mu A mu instead of slash A. And we have seen that in quantum field theory, if we have a classical concept, such as an operator that's given by this classical vertex psi bar A psi here, then in quantum field theory, that gets replaced by the expectation value of the corresponding operator. In our case, that vertex operator, that operator is called a vertex operator because it's a vertex between the three legs, the psi bar, the psi, and the A. So it has in principle 3 coordinates, x1, x2, and x3, corresponding to the locations of the operator psi bar, A, and psi. And that expectation value is calculated in the full theory, giving rise to the full fermion photon vertex, gamma mu. Just as a reminder, the subscript full here refers to taking the expectation value of this operator in the full theory, meaning with the full quantum action, not expanded, not in the free theory. However, it is very difficult to calculate this object in the full theory directly. So what we want to do is we want to expand that result in perturbation theory, so around the point where E vanishes, and we can consider several orders in the perturbation theory. The lowest non-trivial order, that's the first order in perturbation theory, expanding the full action just gives us a term that is S matter times that same operator here. And that gives rise to the first non-trivial correction. We can plug in the result for the matter Lagrangian S matter from equation 42.2. And we find that the non-vanishing correction to the first order perturbative vertex is given by minus I gamma nu integral over expectation value in the free theory psi bar A psi at position x, psi bar x1, A mu x2, psi of x3. Because we are taking the expectation value with respect to the free theory, which is Gaussian, we can use Wick contractions to evaluate that expectation value of this composite operator. And in particular, we will recognize 2-point functions that for the fermions give us the electron propagator, which is always of the form psi bar, or the photon, which is a 2-point function of the gauge field A. So for instance, A mu, A nu. The integral over x then will enforce total momentum conservation at the vertex. And since all of this structure will basically be the same for any order and perturbation theory, we can define an amputated vertex function that just doesn't write these parts, namely the two electron propagators that connect and the photon propagator that connect and the total momentum conservation. This is in complete analogy to what we had in lecture 20 when we were discussing scalar field theory, except that now the field content for QED is slightly richer. It contains both the fermion field psi for the electron and the gauge field A. Just backing up, so basically from doing the Wick contractions, for instance, we can see here there is an electron propagator from X to X1, and then we would have a second electron propagator, but the order of the psi's is wrong. We want to have psi, psi bar, so we have to bring it in that canonical ordering. So we want to pull through the psi through the psi bar here, and since the psi's are Grassmann, whenever we change the ordering of two of the psi's, we'll get an extra minus sign. So we'll get the two fermion propagators, and we change the minus sign here to a plus because we've changed the order of the fermions. So that will give us a plus here, and then we have the three propagators and the momentum conservation. If we disregard those because we just want to talk about the amputated vertex function, all we have left is the coefficient here with the extra minus sign. So we get that to first order in perturbation theory, the connected amputated vertex is just IE gamma mu. That is, of course, the relevant term in the QED Hamiltonian. So basically, we have the first order perturbation theory, the Hamiltonian, be given by the integral over psi bar A mu gamma mu, where gamma mu is now the amputated vertex function times psi, since these are the same thing. And it's not hard to generalize this to arbitrary order in perturbation theory. So basically, in higher orders in perturbation theory, we expect that the Hamiltonian correction has the full connected and amputated vertex function instead of just IE gamma mu in the Hamiltonian. So the upshot is that if we want to calculate the corrections, the quantum field theory corrections to the Landé G factor, we need to calculate the corrections to the fermion photon vertex function. As we'll see, it will be advantageous to work in Fourier space, where the amputated kinetic vertex can be written as a function of two momenta, p and p prime, because of momentum conservation. So in principle, there are three momenta, but momentum conservation restricts the value of the third one. So we only can write it as two momenta, and we choose the two electron momenta to be the ones that we note down as p and p prime. Also, we will find that it will be possible to decompose the connected amputated vertex function in momentum space in terms of two structure functions, which we call F1 and F2. They're called structure functions because the general structure of gamma mu will turn out to be one term that's proportional to gamma mu, and the other term that's proportional to sigma mu times q nu, where sigma mu is the commutator of the gamma matrices. And if we, as you said, choose p and p prime to be the four momenta of the incoming and outgoing electrons, then the difference between two of them is q, and that is the corresponding photon momentum because of momentum conservation. So q will denote the photon four momentum, and p prime will be denoting the incoming and outgoing electron four momenta. And as I said, F1 and F2 are just functions that we call form factors. If we compare to the result that we already have to first order perturbation theory, this one in particular here, we find that there's no non-trivial structure that's proportional to sigma mu, and that means that the structure function F2 to first order perturbation theory just vanishes, and the structure function F1 is just unity. So to first order perturbation theory, we have F1 is 1 and F2 is 0. In general, we can use the Gordon identity that we derived in the last lecture to relate these results of the vertex in terms of structure functions to the Landé G factor. So basically what we do is we use the Gordon identity, we transform to momentum space. So then we get psi bar, p prime, gamma mu, psi of p is -1/2 psi bar p prime of I, p prime mu plus p mu. Those are the Fourier transforms of the derivative operators that we had. And then we have minus sigma mu q nu for the sigma mu term that we had in the Gordon identity. So we can use the Gordon identity here to replace gamma mu in the connected vertex. So let me just go back here. That is the general form. This is the Euclidean momentum gamma e. This is the general form, and we can use the Gordon identity to replace this gamma mu in here. If we do that, then we can write the connected and amputated vertex in a different form, where we write it in terms of the sum of the four momenta p and p prime times the structure function f1, and sigma mu q nu times structure functions f1 plus f2. Now, as before, only the term that is proportional to sigma mu here corresponds to, or gives rise to, the term that will give us the magnetic moment of the electron, because this term here will turn into the spin operator. So the first term we can neglect when we are focusing on calculating the magnetic moment. And that leaves us with the second part, where we'll get q nu a mu that will give rise to our magnetic field here. So what we'll find is that there's relation between G and the form factors F1 and F2 for the connected amputated vertex function to arbitrary order in perturbation theory. And we can use that in order to sort of relate our result for the form factor directly to the G, or the correction of G that we get from the classical result. To do that, recall that when we calculate the energy change from the spin-orbit coupling, we evaluate the expectation value of the Hamiltonian contribution. And since the external B field is assumed to be constant, that implies that the photon momentum that we want to look at is Q is 0. So that means that our G factor is just the factor in front of the corresponding vertex evaluated at Q is 0. And we find that there's relation between G and the form factors, and that is just this simple relation here. The form factors F1 and F2 will in general be divergent. That's a common theme in quantum field theory. We will be able to renormalize the theory, and we know how to do this. We will introduce counter terms for all the parameters in the Lagrangian. And in particular, we'll change the parameter E, the electric charge in the Lagrangian, by E physical plus a counter term, delta E. Once we've sort of done that, we can or have to choose a particular renormalization scheme. We've discussed quite a bit about the MS bar scheme. That's pretty common in quantum field theory. It turns out that for the purpose of QED, historically, the sort of more often used scheme is the so-called on-shell OS renormalization scale. And it is simply given by the condition that the vertex evaluated at Q is 0, so when the photon is on shell, then we want this result to be equal to IE physical times gamma mu. So basically, we can choose a renormalization condition that says that the form factor F1 evaluated for Q is 0 is 1. And that's an exact statement in this renormalization scheme to all orders in perturbation theory. If we choose this particular scheme where F1 of 0 is 1, then we find that the magnetic moment G is given by 2 times now 1 plus the form factor 2 in the on-shell renormalization scheme evaluated at 0. So we can bring the 2 to the other side and find that G minus 2 is just twice the form factor F2 evaluated at Q is 0. So long story short, we find that if we want to calculate the corrections of G with respect to the classical result 2, so we want to calculate G minus 2, all we have to do is evaluate the form factor F2 from the electron-photon vertex in the on-shell randomization scheme, evaluate it at Q is 0 and multiply by 2. That will give us G minus 2. The calculation of the form factor F2 is something we will discuss in the next lectures. And that completes the current lecture.